Hello and welcome to my new series. My plan for it is to build a computer on a breadboard and then program it using assembler at the beginning, but also mixing it with high-level languages like C and C++ later. The final goal is to write a simple video game for this computer step by step. What I'd like to show you in this series is how the processor works step by step, how it talks to the memory and peripherals, how the machine code is read from memory and executed, what are interrupts, how the peripherals catch the CPU's attention, and how it handles the requests, how high-level languages are compiled into the machine code, and how you can mix C or C++ with the assembler, what are calling conventions, and how to mix code from different languages together. You can already find many great videos of people building breadboard computers using the two most popular 8-bit microprocessors, the 6502 and the Z80. I'm gonna use another famous CPU of those times. It started the x86 architecture we were and still are using these days. In the early 1980s, IBM released their first personal computer, which was built using their 16-bit Intel 8088 processor, which is a cost-reduced version of the 8086. Since then, Intel produced many processors in the same architecture, which we still use presently. We had 32-bit CPUs starting with 8386 and more recently 64-bit CPUs. You can see only a few of those from my personal collection. Despite the extremely big technological gap between them and the original 8086, they all still talk in a very similar language. For programmers, it is often very useful to look at the lowest level when debugging their code, even if it was written in a high-level language. I hope that the choice of the CPU we are going to use may help them improve their debugging skills on the PC platform, because once you understand how the 8086 works, you will be able to read and understand the assembler of the newest Intel chips. So, if you don't fully understand what you're looking at now, this series may help you to do that. Before we get our hands on the breadboard, let's first talk about why we have two processors, the 8088 and 8086. They are both really the same 16-bit processor, and both are enclosed in the same DIP package with 40 pins. The only difference between them is the width of their data bus used to communicate with the outside world. The 8086 uses all 16 bits of data in parallel, while the 8088 uses only 8-bit data path. As you can see, the meaning of most of the pins are identical in both cases. The main difference is with pins 2 to 8 and 39. Both versions of the processor, in contrast to the 6502 or the Z80, share the same pins for the address and the data buses. We'll talk about it in more detail later. But while the 8086 uses 16 pins for data, AD0 to AD15, 8088 uses only 8 pins for data transfers. Enough talking, let's start building. This is our 8088 on a breadboard. Before we can power it up and see it in action, we need to make sure that all the power lines are joined together and that all input pins are in the correct state and all output pins we are interested in are hooked up to some LEDs. So first we need to join those VCC and ground lines all together. At the top and the bottom. And also we need to connect together the VCC at the top and the bottom, and then the same with the ground. Let's start with pin 1. It is ground, so let's put it right here. Then pins 2 to 16 are the address and data lines. We'll use some LEDs later to be able to see their states. Then we have pin 17, NMI. That's an input. NMI stands for non-maskable interrupt. We're not going to use interrupts yet. so we need to keep it low. Pin 18, inter or interrupt request. It is active high, so for now we need to connect it to the ground as well. Maybe I'll use that one for a change. Like so. Pin 19, CLK, which is the clock, the CPU's heartbeat. We are going to leave it till last together with pin 21, the reset signal. Pin 20 is another ground. Pin 22, ready, is an input which is active high. It is a signal from the peripheral or memory when it is ready to be read from or written to. We can set it high for now. Pin 23, test, is an input active low. The processor has a special instruction wait which halts execution until this pin is in the active state. Let's pull it down to the ground then. The next 8 pins have dual purpose and their meaning depends on the state of pin 33. That's because the CPU's bus can work in 2 modes called the minimum and the maximum modes. The maximum mode is appropriate for more complex designs where the control signals are generated by an external controller chip. It is required for system using, for example, the floating point coprocessor x86. Our design will be using the minimum mode, which means that pin 33 needs to be held high. After setting the bus mode, we can carry on with the rest of the pins. Pin 24 in minimum mode is called int A, interrupt acknowledge. It is an output active low. Since we're not going to use interrupts for some time, let's simply ignore it for now. Pin 25, ALE, stands for address latch enable. It is an output active high, very important signal which allows us to latch or remember the memory address asserted by the CPU before the same lines are used for transferring data in the next clock tick. You may remember what we said a few minutes ago, that the x86 shares the same pins between the address and data bits. This signal lets us tell them apart. That's why I'm going to put my LED into that signal, which is 25 and the ground. I've got those LEDs already soldered with some current limiting resistors, so we can simply just hook them up. Pin 26 DEN, data enable, and pin 27 DTR, data transmit receive, are output signals. We're not going to use them for now. Pin 28 IOM is an output telling us whether the CPU wants to transfer some data with the memory or the I/O peripheral. That is because, unlike the other CPUs of that time, x86 has a separate address space for the memory and the I/O. The pin selects which one is in use at the moment. It is low for the memory and high for the I/O. In fact, this pin is one of the few differences between the x88 and x86. The latter has this pin inverted for some reason. Anyway, I'm gonna put an LED between this pin and the ground. It will light up when the processor requests access to the I/O address space. It may be useful in the next video. Pin 29, WR, is an output. It goes low every time the CPU wants to write data to memory or the I/O. Let's hook an LED to it. Because we want the LED to be on when the signal is active, we need to pull it up to the VCC. Pin 30 and 31, HLDA and hold, are a pair of pins used to take ownership of the address lines from the CPU by another device on the bus. We're not going to use them, so we just need to pull the hold, which is an input to its inactive state, low. Pin 32 RD is similar to the pin 29 WR. It is active low whenever the CPU wants to read data from the bus. Let's stick a green LED between this pin and the VCC again. Finally, pin 34 SS0 is a status line that we don't need to use. Now we're ready to hook up 20 LEDs to the address and data lines to see a complete state of the CPU bus while it works. I almost completely forgot about the pin 40, the VCC, so the power supply. There you go. This is what we currently have on our breadboard. Now let's talk about the two last signals we need to provide, the clock and the reset. This version of the CPU, ATC88, is a CMOS static design, which means that the clock signal can be arbitrarily slow, so slow in fact that we can generate it with a push button or even pause it indefinitely, and the state of the whole CPU will be preserved. Unfortunately, we can't simply hook up a tactile button to the clock input and expect it to work, and there are two reasons for that. One is the fact that the button would generate multiple impulses every single press due to the vibrations of the pins. We could use a low-pass filter with a resistor and capacitor to filter those vibrations out, but this would cause the signal level to change slowly, and being not a digital really, while the CPU has a strong requirement for the clock signal to have the rising and falling edges very short, shorter than 10 nanoseconds in fact. The solution is this. A simple contraption with a tactile button, the said low-pass filter and the Schmidt inverter 74HCT14 to shape the correct signal edges required by the CPU. I also added a flip-flop 74HCT74, which allows me to switch the clock high and low every time I press the button. This lets me stop the clock at any level I like. Otherwise, when I wanted to stop at a low level, I would need to press and hold the button all the time. I used the similar design for the reset signal, but without the flip-flop. This is the schematic of our computer, together with the clock and the reset contraption on the small breadboard. I think it's time to put things together and power them up for the first time. In order to understand what happens after we turn the power on, let's refer to the datasheet. It gives us three important pieces of information. The first is that to initialize the processor, the reset pin needs to be held high for at least 4 clock cycles. The second is that the falling edge of the reset pin triggers the reset sequence lasting approximately 7 clocks. And finally, the third information is that after the reset, the CPU starts execution from the address of FFFF0 hexadecimal. Before we carry on, I'd like to clarify one thing. During all these videos, my intention is to use the name x86 when talking about the general features which are the same for both processors, like the registers or the instruction set, for it being the original version of the CPU which gave the birth to the x86 architecture. But when I talk about any specific feature of the x88, like for example the width of the data lines, I will mention x88 explicitly. As you already noticed from the pin assignments, the x86 has 20 address lines, meaning that it can address 2 to the power of 20, which is 1 megabyte of memory. In the next video, we will talk more about how it is able to use 20 bits for addressing, being a 16-bit processor, which you would expect to have 16-bit registers. For today, let's just keep it in mind that the first address the CPU will try to read from is FFFF0 hexadecimal, which translates to 16 ones followed by 4 zeros. Okay, I think it's time to power it up. Let's first connect the ground and the power supply to our little breadboard with our clock and reset signals, and also the signals themselves. That is the reset signal, which is 21, so it goes there. If I just move this a little bit so we can see all the LEDs, and also the clock signal, which is pin 19, should go right here. Alright, let's start. Let's power it up, like so. Now the state of the CPU is completely random. We first need to reset it, so that's my reset button, which needs, as you remember, be held for at least 4 clock cycles. So now I can release and wait 7 clock cycles until the CPU starts working. And there we go, something's changed. We've got some address lines active. Just to remind you, the most significant bit A19 is here, then it goes 18, 17, 16, 15, and then from 14 down to A0 at the bottom part of the CPU. So we read the address anti-clockwise like. Do you remember when I said what's the address the CPU tries to read to start its program after reset? It was FFFF0 hexadecimal, which is in binary 16 ones and the least 4 significant bits 0. Let's see, we have 5 high states here. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 ones, and the least 4 are zeros. So there you go. Our CPU 8088 tries after the reset to fetch the first machine code for the first instruction from the address FFFF0. Before we go any further, I need to tell you a little bit more about how the 8086 talks to the other devices on the bus. Each data transfer, whether it's reading or writing, lasts 4 clock cycles. To be precise, it may be more than 4 clocks, because the memory or the I/O device may use the ready signal to make the CPU wait a little bit more for the data if it's not ready. But since we shorted the ready pin to its active state permanently, we will never introduce additional wait cycles. During the first of the 4 clock cycles, the CPU asserts all 20 bits of the address, and the ALE signal becomes active for the latches to store the multiplexed address lines states for the rest of the whole transfer. Then, during the second cycle, the multiplexed address and data lines become the data lines, and they are inputs or outputs depending on the data direction. One of the RD or WR becomes active, again, depending on whether the CPU wants to read or write the data. Then, in the third cycle, the CPU gives the memory or the I/O device time to get ready to be read from or written to for another cycle. The last 4th clock cycle makes all the control signals and the address data lines inactive. Then the whole process can repeat if the CPU requires to transfer more data. We saw the processor addressing the memory in order to fetch the first byte of the program after reset, but currently we have no memory which would return it to the CPU, so the outcome would be unpredictable. What we could do is to use one machine code called NOP, or no operation, which, according to its name, does nothing, still being a valid instruction. We can't, of course, just tie the data to either ground or the VCC to simulate ones and zeros, because the lines are multiplexed and are also used as outputs for addressing. What we could do, though, is to use resistors to pull them up or down, but without short-circuiting them. This would simulate the memory, returning the bits every time the processor expects the next program byte on the data lines. I'm gonna form the NOP opcode, which is 90 hexadecimal or 10010000 in binary, using 8 resistors between each data line and either ground or the VCC. Let's get to work. Just to be able to easily hook up those resistors, I first extended those AD0 to AD7 lines just to the right hand side to be able to more easily put those resistors. Remember, NOP, no operation, is 90 hexadecimal, which is 1001 and then 4 zeros binary, so the most significant bit is 1. Therefore, our resistor first resistor goes to the VCC. Then we have 2 zeros. That is one of them. Then we have another 0. The next bit is 1 again. So that goes to the VCC. I'll need to be careful not to short circuit them. And then 4 zeros, the least significant zeros. 1, 2, 3, so that would be the bit number 1. And bit number 0, AD0, the least significant bit, goes there. Quick double check. 1001, and then 4 zeros. Okay, I guess it's time to power it up. And again, as you probably remember, now the CPU is in a random state. We need to first reset it for at least 4 cycles. Then I can release the reset button and go through it approximately 7 clock cycles before it's ready to work. And it looks like it's reset. Now let's see, our LEDs show F, 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 F0. The last 4 bits are zeros, as expected. And additional information that this is an address on the bus is the yellow LED, which is connected to the ALE address latch enable signal, which is active high when we have the address on the bus lines. Okay, that's our first of 4 clock cycles. Let's go to the next one. So 1 and 0 here, okay. What we see now is the A8 on up to A15 are still holding the part of the address because they are not used for transferring any data, and the most significant 4 bits are holding some status which we're not gonna read, we're gonna ignore for now. But look what happened, and these 8 least significant bits, which are, remember, shared with address and data. Currently in the second cycle of the 4 all cycles of the bus transfer, these are data lines. And as you can see, our resistors pulled up or down the 8 bits here accordingly to what we wanted to achieve. So we wanted the NOP machine code, which is 1001 and then 4 zeros. So what CPU sees now is our memory simulation. Those resistors pulled up and down all the 8 bits to form the byte, which stands for the no operation instruction for it. And also, as you can see, this green LED is on, which means that RD read signal is active, meaning that the CPU is trying to read from the memory. Okay, so that's the second cycle. The third cycle doesn't show much on the LEDs, not much changed, but that was the moment when the CPU accepted what's on the data lines and read our NOP or no operation machine code. The fourth cycle then just turns off the RD signal, and our data lines are still set to 90 or 10010000. Okay, and that was the first fetch of the instruction after reset. So then we go back to the first cycle of the next fetch, and as you can see, all the address lines are now active. ALE shows that this is the address, but what's changed? Look at the least significant bit. Now we have FFFF1, because NOP instruction does nothing, so our CPU tries to fetch another instruction, which is in the next byte. So now it tries to read from FFFF1 another instruction. So it will see NOP again, 10010000. That's the third and the fourth cycle of this transfer. RD is now inactive, and that is the third fetch. And as you can see, now the CPU tries to read from FFFF2, so it tries to fetch yet another instruction from our memory, and now that means that it tries to read. Now it read it, and it goes to yet another fetch. Now we've got FFF3 addressed, and it's a read, and of course it reads another NOP. That's it for today. I hope you enjoyed it. If so, please leave a thumbs up and subscribe to get notified about the next video, in which we will attach a flash memory chip and write the first real program for our computer. Thank you for watching, and I'll see you next time.